Hi folks! The following video is going to talk more about equilibrium position for Bronsted-Lowry acid-base reactions. I'll talk about the leveling effect, counterions, and a different definition of acids and bases known as Lewis acids and bases. Recall from last time that I talked about 4 different qualitative factors that allow us to rank acidity. These 4 factors, in order of priority, are the atoms of the conjugate base. If your conjugate bases have the same atoms involved, then you turn next to looking for resonance. The next biggest factor after resonance to look out for is inductive effects, or induction. And the last ranking factor to look for are the orbitals involved in your conjugate base, or rather the atom's hybridization. In terms of predicting the position of equilibrium for a Bronsted-Lowry acid-base reaction, if you know pKa's, you can use them to determine this position. So let's consider a reaction between a carboxylic acid and the conjugate base of an alcohol. This anionic species can be known as an alkoxide. To predict the products, I'm going to show the curved arrow mechanism. The products this would form are the deprotonated conjugate base of the carboxylic acid and an alcohol. You want to identify your acid and conjugate acid and see if you know those pKa's. The pKa of the carboxylic acid is about 5, and the pKa of the conjugate acid, this alcohol, is 16. Our equilibrium is going to favor the side with the higher pKa, or the weaker acid. I could redraw my equilibrium arrow to indicate that this reaction would favor the product side. Now let's consider another example. What about this equilibrium below? I have a neutral nitrogen with a hydrogen on it next to a CO double bond, compared to a nitrogen with a negative charge next to a carbon-sulfur double bond. And on my product side, I've added the hydrogen to the nitrogen next to the carbon-sulfur double bond, and now the nitrogen next to the carbon-oxygen double bond is negatively charged. So if I'm only relying on pKa's, I'm going to run into trouble here because I don't know the pKa of my acid or my conjugate acid. Instead of looking at the acids, we'll turn our attention to the base and the conjugate base, and we're going to look at our 4 factors that influence how stable a base is to determine which side is favored. The side with the more stable base will be favored. Here I've just redrawn the same equilibrium from the previous page, so the first thing to do is identify the base and the conjugate base. I like to do this by drawing the curved arrow mechanism. I draw my curved arrow from the nitrogen lone pair with the negative charge to hydrogen, break the NH bond, and bring the electrons to nitrogen. The atom that's using its lone pair to deprotonate the NH bond is the base, and the molecule with the nitrogen with the negative charge on the product side is the conjugate base. Next, I need to compare the stability of my base to that of the conjugate base. I've redrawn the structures below. I'm going to go through my 4 different factors in order, looking for differences between my 2 molecules. The first factor is atoms, and I'm looking particularly at the atom that got the extra lone pair, and in this case the negative charge. I'm comparing a nitrogen to another nitrogen, so I have the same atoms in each case. Since I have the same atoms, I need to move on to my next factor for comparison, resonance. Each of my molecules has resonance, so I need to draw the resonance and the other resonance contributor to compare them. I have the same type of resonance in each case, lone pair adjacent to pi bond. My resonance pattern is I bring the lone pair down to form a pi bond, and I break the pi bond and form a lone pair. In my second resonance form, in each case I have a carbon-nitrogen double bond, but now I either have a carbon single bond to sulfur with a negative charge, or a carbon-oxygen single bond with an oxygen with a negative charge. Notice now I'm comparing two different atoms with negative charge, sulfur versus oxygen. You want to look at the periodic table to determine where these atoms are relative to each other, and sulfur is in the same column as oxygen, directly below it. Because it's lower on the periodic table, sulfur is larger than oxygen. And the larger the atom is, the more spread out the negative charge is, and the more stable that atom is with the extra electron pair that the base has, compared to the acidic form. This means that my molecule with the sulfur in it is more stable than my molecule with the oxygen in it. Going back to my reaction equation up above, this means my base is more stable than the conjugate base. My equilibrium favors the side with the more stable base, so in this case my reactants are favored. I would draw my equilibrium arrow longer pointing toward the left to reflect this. Another way a question could be phrased is, for example, is the following base with a carbon with a triple bond and a negative charge strong enough to deprotonate an alkene? You want to begin by drawing your equilibrium. The base and the acid you're given are your reactants, and then you're going to draw your curved arrow mechanism and draw the products. I'm using the lone pair from my base to deprotonate a carbon-hydrogen bond of my alkene. This gives me an alkyne, which now has CH bonds on either side of the triple bond, and I have an anionic molecule with a carbon-carbon double bond. The next thing you'll want to do is identify the base on either side of the equilibrium. My base is the anionic molecule with the carbon-carbon triple bond, and my conjugate base is the anionic molecule with the carbon-carbon double bond. Next, you want to compare the stability of the two bases. I'd start by looking for the atoms involved. Notice that my extra electron pair here resides on a carbon in either case, so the atoms are the same. I would next want to look for resonance. Neither of these molecules has resonance. Next, I would look for inductive effects, but I don't have any polar bonds near my conjugate base in the molecules, so I don't have inductive effects. And then last, I'd look at the atoms or hybridization involved. Here I do have a difference between my base and conjugate base. The carbon with the negative charge of my base is sp hybridized, and the carbon with the lone pair of my conjugate base is sp2 hybridized. sp orbitals are smaller and held more tightly to the nucleus compared to sp2 orbitals, meaning having an extra lone pair in an sp orbital is more stable than having a lone pair in an sp2 orbital. I'll now look back at my original equation, and the equilibrium is going to favor the side with the more stable base. My base here is more stable than my conjugate base, and then I can redraw my equilibrium arrow to reflect this. I would expect my reaction to favor the reactants side rather than the products. And so, to answer my original question of is that base strong enough to deprotonate an alkene, I would say no, it's not. Because the equilibrium favors reactants instead of products, that base isn't strong enough to favor the deprotonation of an alkene. I want to talk about a factor known as the leveling effects, and I'll address it for both acids and bases separately. The takeaway of the leveling effect is that your choice of solvent really matters. For an acid, the acid will protonate the solvent if the acid is a stronger acid than the conjugate acid of that solvent. So you have to think about both the acid as well as the solvent you're using it in. Let's consider an aqueous solution of sulfuric acid. Here I would have H2SO4 and water present. I want to show the curved arrow mechanism. Here I'm using water as my base to deprotonate sulfuric acid. The products of this acid-base reaction would be HSO4-, the conjugate base of sulfuric acid, and H3O+, the conjugate acid of water. To predict which side of the equilibrium is favored, I'm going to use pKa values because those are ones from my table. The pKa of sulfuric acid is -10, and the pKa of H3O+ is -2. My equilibrium favors the side with the higher pKa, or weaker acid, so I would expect my product side to be favored here. In fact, the equilibrium doesn't just slightly favor the products, it strongly favors them. Looking at my difference in pKa values, I can conclude that sulfuric acid is 10 to the 8th times stronger than H3O+. What this means is that the second you dissolve sulfuric acid in water, it gets deprotonated to form HSO4- and H3O+. As soon as you mix it, there is essentially no H2SO4 left in that form. Given that every acid that's stronger than H3O+ will react with water to form H3O+, H3O+ is the strongest acid that can be present in water solution. This is what's known as the leveling effect. You put in a stronger acid, but it reacts with your solvent to form a weaker one. We can also have leveling effects involving bases. In this case, a base is going to deprotonate your solvent if your base is stronger than the conjugate base of the solvent. So let's consider an aqueous solution of NH2-. NH2- is a strong base, and I'm going to consider it deprotonating water. This acid-base reaction would form NH3 and OH-, known as hydroxide. To predict which side of the equilibrium is favored, I'll compare the pKa of the acid, water, to the pKa of the conjugate acid, NH3. Based on these pKa values of 16 versus 38, my equilibrium is going to strongly favor the right side. So I'm going to redraw my equilibrium arrow facing longer to the right. What this means is that the minute that you dissolve NH2- in water, it's such a strong base that it will deprotonate water to form OH-. As soon as you mix the two together, you'll have essentially no NH2- present, and it'll all get protonated to form NH3. The strongest base you can have present in water is OH-, known as hydroxide. Any base stronger than this reacts with water to form hydroxide. This is our leveling effect for bases. If you want to use a base stronger than hydroxide, It's not impossible, it just means that you can't use water as your solvent. Some other suitable solvents that are used instead contain carbon-hydrogen bonds instead of oxygen-hydrogen bonds, which gives them a higher pKa. Some examples are hexane, THF, and diethyl ether. I now want to talk about counterions. Anytime you have an anionic molecule, such as a negatively charged base, it's always accompanied by a positively charged molecule known as a cation. We can't really have a molecule with a charge that isn't being balanced out. For example, I'll commonly draw just OH- or another anion, but in reality, it's accompanied by something else. For example, being present in the form NaOH, KOH, or LiOH. Here, the sodium, potassium, or lithium, each with a positive charge, are counterions. These are sometimes known as spectator ions. These stabilize the base by providing a balance of charge, but they are not going to react in our acid-base reactions. So if you see a cation, ignore it and just focus on the base instead. So if I drew a reaction, NaNH2 plus water goes to form NH3 and NaOH. For our acid-base reaction, we're really just looking at NH2- reacting with water to form NH3 and OH-. So sometimes I will draw the counterions, sometimes I won't, and same for the textbook. To end, I want to talk about our new type of definition of acids and bases, known as the Lewis definition. This is more general than the definition of Bronsted-Lowry acids and bases, where we're talking specifically about transfer of a proton. A Lewis base is any electron pair donor in a reaction, and a Lewis acid is the species that accepts the electron pair. So we could consider this reaction where I have an ether reacting with BH3. BH3 has an incomplete octet, and oxygen has 2 lone pairs, one of which it can donate to form a new bond to boron. Lewis acid-base reactions are going to have one curved arrow. It goes from a lone pair to an atom. This curved arrow is showing oxygen sharing its electrons to form a new oxygen-boron bond. In the product, we have to think carefully about charges. Notice in the product, boron has 4 bonds, and since it has 3 valence electrons, this gives it a -1 formal charge. And an oxygen with 3 bonds in a lone pair has a positive charge. To classify my molecules, my Lewis base is the one that is donating its lone pair. The Lewis acid is the atom, in this case boron, that is accepting the lone pair. And the product that's formed upon this reaction can be known as a Lewis acid-base adduct. Your curved arrow always goes from a lone pair on the Lewis base to the particular atom that has an incomplete octet. Anytime you see BH3, remember that it has an incomplete octet and an empty p orbital. This Lewis acid-base reaction allows the boron to obtain a complete octet. In summary, I talked some more about predicting the equilibrium position for Bronsted-Lowry acid-base reactions. I talked about the leveling effect for acids and bases, counterions, and the Lewis definition of acids and bases. That's it for this video. I will see you in class.